In this video, we're going to explore some basic theorems related to chords and radii of a circle. So we've already looked at some vocab, and in the vocab, again, we've defined what a circle is, radius, tangent, and all that other good stuff. Here we have a theorem that we have two chords, chord AB and chord CD. And I'm going to move these chords around a little bit and just kind of play around with these guys here. And what I want to do is I want to be in a situation where these chords are going to be the same length. So it looks like I'm going to have to either make AB bigger or CD smaller. Let's make AB bigger. I'm trying to match up the lengths of the two. Here we go. And what I'm trying to see is there a relationship between the segments here, OM and ON? And on first glance, it appears that they might actually be the same. Well, let's see if that's right. It's pretty close. We're within the 100th of them being actually the same. Let's move some things around and see if that still works. CD, I'm going to call that 7.25, and AB, pretty darn close. OM and OM still are the same. So what we end up having here is a relationship between our chords. And what that relationship is if the chords are congruent, then that means that they're the same distance away from the center of the circle. So we're going to make a conjecture here. And again, a conjecture is just a mathematical argument about something. If chords are congruent, then they are the same try that again. Same distance from the center of the circle. So in practical terms, what that means then is we're going to take some diagrams here. I'm going to move my screen. There we go. And we're going to apply this theorem, that if the chords are the same length, then they're the same distance from the center. So finishing the statement, if AB, so that's our chord here, and CD are congruent, then what that means is that they are the same distance from the center. So then EF has got to be congruent to EG. Similarly, if we had the reverse, if we knew that FE was congruent to GE, that tells me the chords are the same distance from the center, then they also must be congruent. AB is congruent to CD. So let's put some algebra to it. If we know that QV is congruent to QW, so that means that our chords are the same distance away from the center, then it also is going to tell us that the chords are equal. So in number 8, if PT is 13, so that's this chord right here, then we know RS is going to have the same measure. It's going to be 13. And on number 9, if PT is 2x minus 3, find RS is x plus 6, find the value of x. Again, they're congruent chords because they're the same distance from the center. So I'm going to set those equations equal to each other, and I'm going to solve for x. And I get 9. And 10 is the same thing, it's just a different variable of k. 11 and 12 are the reverse. We know that the chords are congruent, so then that means that these two segments are congruent because they're equidistant from the center. So I'm going to take EF, which is 3x plus 1, and set it equal to EG, which is 5x minus 5. And I want to solve for x, so I'm going to bring my 3x's over and bring my 5 over. So x gives me 3. So that's essentially the idea of that first activity. Now we're going to look at another activity, another sketch in GeoGebra, where we have a radius and a chord are going to be perpendicular. All right, now we got it all lined up. So it says, note that line segment AG is perpendicular to chord EG. So we've got a right angle there. Move point A until AG passes through the center of the circle. So essentially what we want to do is create a larger radius of sorts. And I can put A pretty much anywhere, but I'm going to put it on the circle, and I'm going to have it go through the center. So that's going to create essentially a diameter. Now, if I show the segment lengths here, what appears to have happened to the chord, it looks like it's been bisected. We've been pretty close to being accurate on this. Might be able to zoom in. Yep, I'm a little off from my center. Now it's a little more lined up. So when the radius is perpendicular to a chord, it seems like we've got this relationship where the chord is going to be bisected by that radius. So our conjecture in this case, sorry about this, got to keep moving the screen here. There we go. If a radius is perpendicular to a chord, then it's, or well, let's call it the radius, then the radius bisects the chord. So in a question like this, we draw CA. CA is considered a radius of C. Oops. Try to draw a better radius there. All right, fair enough. CA is equal to 10, so I'm going to go ahead and put 10. CD is equal to 8, so I'm going to go ahead and put 8 in there. We want to find the length of chord AB. Now, you might say that CD is actually not a radius, and you're absolutely correct. It's not a full radius, but it is part of it. If we were to extend that out, we would see that CD is part of that radius. So it is going to be perpendicular to the chord. What that means then is it's going to cut that chord in half. So if I'm looking at this as a right triangle, which it completely is, I can solve that right triangle by finding the missing piece here using a triple, 6, 8, 10. And so that larger chord, because this radius is perpendicular, it's going to bisect it, gives me 6 and 6. So the chord then would be 12. And 6 is the same idea, but we haven't drawn in a lot of the stuff for you. Now we're saying draw in radius EG. EG is 13. The chord is 24. And we want to find the distance from the center of the circle to the chord. The way we're going to do that is we're going to draw in this radius so that it's perpendicular to the chord. And we know the chord is 24, so this gives me 12 and 12. And so again, we've got a triple. 5 is my missing piece. So that is the length, or sorry, the distance from the center to the chord. And the third approach of this, and it's the same type of thing, we have chord PR is 8 units from the center of the circle. So I'm going to draw this in. I'm going to, again, draw a radius and perpendicular. This is 8. PR is 30. So again, I know a radius perpendicular to a chord will bisect it. And we want to find the radius, so we're going to draw the radius in. And we get 17, completing the triple. Now, connecting what we've already done, if we have a segment or a question like this, we've got given circle G, BG is congruent to EG, AC is 2x plus 6, and DE is 3x minus 7. So again, we know that these two parts are congruent. If that's the case, then the entire chords are congruent. But take a look at what else we have. We have the AC, the whole chord is 2x plus 6. But DE, we only have part of it. We don't have the whole thing. We only have the smaller chunk. Well, this radius, or this part of this radius, is perpendicular to a chord, so it's going to bisect those pieces. So all of those marks with 2 are going to be exactly the same. So if I'm looking at AC compared to DE, DE is half of AC. So what I can do is take my measure for AC and set it equal to double 3x minus 7, which is the measure of DE, because doubling it gives you the entire segment, DF. So I've got 2x plus 6 equals 6x minus 14. And I can solve for x by bringing the 14 over, giving me 20, and at the same time bringing the 2x over, giving me 4x. X is 5. Now, if I want to find DF, I have a couple choices. One is I can plug 5 in for DE and double it. Or if AC and DF are the same, I can just take the measurement, 2x plus 6, and plug 5 in. So again, two theorems today about chords. One is that if the chords are congruent, then they're equidistant from the center. And the other is that if radius is perpendicular to a chord, it's going to cut the chord in half, bisect it.